Hi. So I wanted to talk about this recursive formula for the number of derangements of n objects. This one right here. Okay, so first, let's just see what I mean by a derangement. So there's this question. Inez's swimming team consists of n people and they all have their own locker labeled with their names. Inez is feeling a little sneaky and wants to rearrange the name labels in such a way that no locker has the correct name label. Suppose that the number of ways Inez can do this is dn. So this number dn is what we call a derangement of n objects because there are n lockers that need to be labeled. So more generally, the question is, how can we permute n numbered objects such that no object sits in the position that it's numbered with? So if we think about the numbered objects as just the numbers 1 to 5, 1, 2, 3, 4, and 5, let's have a look at how we can derange these objects. So one thing I can do is I could just cycle them all the way around. So I could move 1 to 5, move 5 back and 4 back and so on. So that would be 1, 5, 4, 3, 2. And now none of these numbers are in its original starting place. So none of these numbers are in the position that they are numbered. Or I could just cycle the first 3 and then swap the last 2. So I could go 5, 4, and 2, 3, 1. Okay, and let's have a look at how we can prove this recursive formula. So if you're just given this as a question and you want to figure out why this recursive formula is true, then I think it's instructive to notice that you've got this quantity here, n minus 1, multiplied with this sum of 2 terms over here. And so that gives me the impression that we're going to be using what we call the multiplication principle. Multiplication principle. So what I mean is, so when I say multiplication principle, what I'm referring to is this idea that if we've got, let's say we're considering the weekend, Saturday and Sunday. And on Saturday, I've got 3 choices of fun socks to wear. So I've got red, green, or blue socks that I can wear. And then let's say that on Sunday, I'm going to be boring and I'm going to have either black or white socks. So we consider the number of options that we have for Saturday. And because I can wear either red, green, or blue, I've got 3 options for Saturday. And for Sunday, I've got 2 options, black or white. And so if the question is, what is the number of combinations of sock wearing that I can have for this weekend, then we multiply the 2. And that's because for each choice of red, green, or blue, I can have either black or white socks for Sunday. And so let's say I pick red on Saturday, then I've got black or white on Sunday. That's 2 choices. And then another 2 choices for if I pick green on Saturday, black and white for Sunday, or if I pick blue for Saturday, and then I've got black or white for Sunday. And so that's 3 lots of 2, which is why the total number is 3 times 2. So I know that's a really simple example, but we're going to be considering cases in a similar way in order to figure out why this is true. Okay, so another thing I wanted to talk about was this plus here. So I've talked about the times, and this plus gives me the impression that in each of these n-1 cases, there are going to be further cases to consider. And I think in one of those cases, I'm going to be counting up this number of possibilities. And in the other case, I'm going to be counting up this number of possibilities. So let's have a think. How might I get n-1 cases? Well, I think it's pretty useful to think of the n lockers and think about the number of options for any one of these. So if there are n lockers here, and then without loss of generality, I consider the first locker. So all I know about this first locker is that I can't put the first label in this locker, so I can't have this situation. Okay, so that means that for the first locker, I've got n-1 other options to put in there. And I think that could possibly be the basis of our cases. And hopefully we'll find that the number of derangements for each n-1 amount of options for our first locker is going to be exactly this quantity here. Okay, so I've got n-1 options. Let's just suppose that locker 1 gets the nth label, so capital N. Okay, so that means that I'm going to put the nth label on locker 1. Now I want to see that, I want to prove that now the number of derangements where this happens is dn-2 plus dn-1. And let's pretend that this locker here is actually the nth locker. So there's one simple case, which is where, well, 1 now has n's label. Where does 1's label go? So a simple case is if 1's label just goes to n. And so 1 and n just swap with each other. And in order for a derangement to qualify under these conditions, we just need the rest of the lockers to be deranged as well. And we can actually consider taking away the n and the 1th lockers that have just been swapped. And the number of ways to derange the rest is exactly dn-2, because we've just taken away the 2 lockers that have swapped with each other. So for each option of the first locker, and we're going to name those options with this capital N, then the number of derangements has definitely at least this amount. This happens when n and 1 swap. So I just want to prove that when n goes to locker 1, the rest that I have to count is exactly dn-1. So let's think about what case this should correspond to. And so what I haven't considered is when 1 receives the nth label, but n does not receive the first label. And so I've got a situation that looks something like this. This is the first locker. And then a bunch of lockers, and then the nth locker, and then a bunch more lockers. So I've got that n has gone to 1, but then 1 now goes to either of these positions. Maybe even the last one here. And now n receives either one of these. Okay, so this is a little weird because it's not as nice as the other case where it just sort of became closed after we removed the two lockers that swapped with each other. And the question just became smaller and we could count using what we've already counted. So for this question, we're going to want to find out how we might possibly get dn minus 1. Unfortunately, it's not as simple because we've got this cyclic behavior. We've got that n has gone to 1, and then we've got that 1 has gone to something else. And so I can no longer just remove something. It would be perfect if I could just remove exactly one of these lockers and then reduce the question to a derangement of n minus 1 objects. But actually, there's a little clever way we can do this. Okay, so let's suppose that I need to count how many ways I can get a derangement where n goes to 1 and 1 goes to something else that is not n. Okay, and I can actually count this up pretty quickly by performing this sort of transformation or conjugation. So conjugation is basically when you transform the problem into something that's a little easier. Find a way to answer the question and then transform it back to the original. So the transformation that I want to make now is swap the labels on lockers 1 and n. And you'll notice that if I do that, okay, so I'm going to just swap in purple. Now, if I do that, then n receives its own label back. And okay, so what I want to do is temporarily swap the labels. Temporarily swap the labels on lockers 1 and n. See if I can find a derangement after I've done this, such that when I swap them back again, so when I swap the labels on lockers 1 and n back to their rightful label, then what I get is also a derangement. So if I temporarily swap 1 and n, so I make n temporarily hold its own label, then the condition I have on 1 is that 1 does not receive the first label. 1 doesn't receive its own label. And why do I want that? Well, if 1 did receive its own label, then when I swap them back, I get this situation here. I've got 1 has label n and n has label 1. And that's not what we want. We don't want to be counting this sort of derangement because we've already counted this sort of derangement in this case here, when n and 1 swap. So in this case, where I've got this cyclic behavior, n goes to 1 and 1 does not go to n, but it goes to something else, a derangement with these labels wouldn't qualify as something I want to count in this case. So that is my only condition on 1. If there's any other label, then I'm all good. Like if I get the label 2, then after I swap 1 and n again, then n will get label 2. And that is allowed. That is a derangement that I want to count. Okay. So what about the rest of them? What are the conditions on the rest of the lockers? Well, you'll notice that this temporary transformation we've done, swapping the labels on lockers 1 and n, doesn't actually affect what I choose to do to the rest of the lockers. Because the rest of the lockers are not included in 1 and n. They're not included in this transformation. So if I want the resulting thing to still be a derangement, then I've just got the same conditions that I needed originally for things to qualify as derangement. So basically, 1 cannot go into 1, as we've just discussed. And as normal, 2 cannot go into 2. 3 cannot go into 3, and so on. And so what I've got here is a situation in which n holds its own label. Okay, so I can just pretend that's not there. Pretend it's not there. And then I've got how many other lockers? I've got exactly n minus 1 lockers left. And what I'm asking is, how can I put labels in them such that no locker receives its own numbered label? And the number of ways in which I can do that is dn minus 1. Awesome. So just to recap, in this case, we're asking what's the number of derangements such that n goes to the first position and the first label does not go back into the nth locker. And the way we've counted that up is by doing this quick little transformation, this temporary transformation where we swap the lockers 1 and n. So because the nth label has gone into the first locker, when we do this little swap, the nth label temporarily holds its own label. And then the conditions on the rest of the lockers to qualify for a valid derangement at the end is just the same as any other derangement. We've got that every locker cannot receive its own label. So I count dn minus 1 many ways that I can do this. And then once I get a derangement on the rest of them, then I swap the labels 1 and n again, and I've ended up with a valid derangement. Okay, I hope that made sense. Yeah, so now this is addition, and it actually exhausts all the possibilities because it's either that n and 1 swap or n and 1 do not swap. So for each of the n minus 1 options in the first locker, we found dn minus 2 ways in which n and 1 swap, and dn minus 1 ways in which n and 1 do not swap. And if we put everything back together using the multiplication principle, it's just n minus 1 choices for the first locker. So there are n minus 1 possibilities of what this prenumeral n represents in my above proof. And then for each of those choices using the multiplication principle, I've got dn minus 2 ways when n and 1 swap, and dn minus 1 ways when they do not swap. And that is the final answer.